Okay, so I went actually to Australia initially to study lunar glasses and lunar volcanic processes, but that project shrank quite quickly due to acquiring samples from NASA, and there were some issues. So I changed during I was there the focus of my research on looking at how volcanic gases interact with silicates. And that started with looking at minerals and also melts. And we then decided to look specifically at very simple silicate glasses, because there are so many different variables that might affect these reactions that we decided we need to simplify things. So why do we care about sulfur dioxide? Sulfur dioxide is one of the major sulfur-bearing volcanic gases throughout the solar system. Wherever we have some sort of volcanic activity, usually we find a lot of sulfur dioxide. This is the case on Venus. It's the case on the Jupiter moon Io, where a lot of sulfur-rich gases are emitted in explosive eruptions, sulfur dioxide and other sulfur gases. On Mars, it likely was the case. There is no active volcanism there at the moment, but a lot of the surface materials are very rich in sulfates, and at least some of them likely originated from interactions with sulfur dioxide, reactions that I will talk about today. And then on Earth, sulfur dioxide is the major sulfur-bearing volcanic gas species. For example, this is a volcanic gas, the speciation of a volcanic gas from Ale volcano in Ethiopia. On the x-axis on this plot you see the temperature from 500 to 1500 degrees Celsius, and on the y-axis you can see the mole fractions of the different gas species. This is just to give you an example. It's pretty much the same, more or less the same, for all terrestrial volcanic gases, where we have first H2O, followed by carbon dioxide, and then sulfur dioxide. The second most abundant volcanic gas species with sulfur in it is usually hydrogen sulfide. This shows the importance of sulfur dioxide, and in addition of those three gases, sulfur dioxide is the most corrosive and aggressive. Hence we are looking first at this particular gas to look at reactions with silicates. So where might we expect interactions with silicates? Silicate glasses in volcanic ashes are erupted together with a mixture of volcanic gases, and people like Paul Iris at Munich and Paul Delmel in Belgium have looked at how volcanic ashes can scavenge sulfur dioxide and HCl and other gases, volatile species, onto the ash particles. And this reaction with sulfur dioxide is what I will talk about today. So globally, there is an emission of about 10 megatons of sulfur dioxide per year, but usually it's the very large individual eruptions which can change that, or which can emit much more on their own in a single eruption than globally in 1 year. So we have this reaction occurring, as I mentioned, on different planetary bodies, and we have them occurring in explosive volcanic eruptions. And we also have sulfur dioxide gas, of course, in the subvolcanic environment, and that's where I've been quite interested in. If we look at where we might expect some sulfur dioxide, we have to look above the pressure conditions where the sulfur dioxide is released from the magmatic reservoir. That's usually at a depth of 3 to 6 kilometers, where the gas, together with other volatiles which are released at high pressures, such as CO2, forms a gas that forms a volume. We call that the gas core, at which the pressure of the gas is higher than the hydrostatic pressure of the surrounding water. And in this gas core, we have very hot temperatures, we have a fairly high flux of gases, and we can measure the end product of reactions that happen coming out at the top, where they are emitted at temperatures of up to 1100 degrees Celsius, such as at Erta-Ale. Coming from Australia, you always have to talk at least a little bit about mining relevant topics. So incidentally, this pressure temperature area in subvolcanic environments where we have this high temperature volcanic gas is where we form porphyry copper deposits. Why do we talk about gases under these conditions, or at least low density fluids? Is because those fluids actually behave more like a gas than a fluid. This is a plot, temperature 500 to 1100 degrees Celsius, the y-axis pressure from 0 to 100 MPa, and this green box shows the conditions at which we find fluid inclusions in porphyry copper systems. On top of this, we can see in blue lines of fluid density. So here are conditions where we form most porphyry copper deposits. The fluid has a very low density of less or roughly a tenth of liquid water at the surface. That's one of the properties which suggests which is why we talk about gases or low density fluids. Second one is a property called the dielectric constant. The dielectric constant is a property which is also called the relative permittivity, and it's a property that describes how a molecule behaves, what's the polarity of molecules, and how easily does it form clusters or liquids. So a high dielectric constant results in high polarity molecules, such as H2O at 1 atmospheric pressures and temperatures. But at these conditions here, those dielectric constants are very low, suggesting that they behave like individual molecules which don't interact with each other as much. Hence, they're more independent, form less clusters, and behave more like a gas, an ideal gas, than a fluid. Okay, so that's.
So what kind of fluid is this? Water or?
This is just water.
Water, okay.
So, what reactions do we expect? This is sulfur dioxide reacting with anorthite. If we have anorthite plus sulfur dioxide, the calcium goes into a sulfate, such as anhydrite. It leaves some sort of aluminosilicate. I'm not talking specifically about any phase here, but a calcium depleted aluminosilicate material, and we produce some free sulfur radicals, because if we react sulfur dioxide with a silicate, we get a disproportionation reaction from a 4 times positively charged sulfur atom in the sulfur dioxide to a 6 times positively charged sulfur atom in anhydrite. And to charge compensate, we also need to produce some reduced sulfur radical. In the presence of water in a more natural system, this reduced sulfur forms hydrogen sulfide. And this hydrogen sulfide is particularly important in porphyry systems because it provides the reduced sulfur to deposit the metals. Conventionally, people have been using this equation here, which is a simple gas buffer reaction of sulfur dioxide reacting with H2 gas to form hydrogen sulfide and water. But it turns out that if you have calcium-bearing silicate present, you can actually form this reduced sulfur molecule up to 10 times more efficiently and faster than with the classic buffer reaction. So if you have a reduced sulfur molecule in the gas, we can then look at the metals that are transported with the sulfur dioxide. Usually, again, these are plots of the speciation of these metals. 500 to 1500 degrees Celsius at 1 bar pressure, showing the speciation in mole fractions from 1 to 10 to the minus 6 mole fractions. The solid lines are solid metal species, and the dotted lines are gas species. So we have the most abundant metal gas species are in all cases that matter to porphyry copper deposits, at least chlorides. So as we have the chlorides, we can add in our reduced sulfur, our hydrogen sulfide, and we deposit things like chalcopyrite or bornite. And to show you why this is an important reaction, we can go and look at, for example, the Grasberg porphyry copper deposit, one of the world's largest copper and gold deposits. And when we look at drill cores which are deep enough where the sulfate is not dissolved by surface waters, we find associations next to each other of here the sulfate, the anhydrite, and next to it the sulfides. We have some chalcopyrite and some bornite in there as well.
So, sorry, where do the chlorides come from? Did you say? Maybe I missed it.
They're from the volcanic gas. So,
okay,
so
so
this,
they are,
yeah. So this.
They come out from the chamber.
Yes.
Like that.
Yeah.
Okay.
How they come out with the metals or not is an open question that
Okay.
I'm very interested in, but we don't know. So this was a model, a Gibbs free energy minimization model, taking this Oerter-Ahle volcanic gas composition and simply adding very, very low amounts of metals, and then doing the calculations and looking at how they speciate in that particular gas.
Mm-hmm.
So we've seen that sulfur dioxide is a major volcanic gas species in a range of planetary bodies. It can react with silicates in a range of environments in atmospheric pressure conditions, such as in explosive volcanic eruptions, but also in a subvolcanic environment where we can observe these reactions in porphyry copper deposits. So the aim of my study was to look at very simple systems to try to figure out what is the reaction mechanism, how fast do these reactions occur, what properties of the silicates, for example, might affect reaction rates, and then later on also what happens if we have metals in the glasses themselves.
So just to move on, so how those people decided those are the reactions that should happen? I mean, you can probably imagine all sorts of reactions, right?
Yes, so you can look at rates,
Yeah.
and you can compare the different rates of those reactions,
Yeah.
and that's how this estimate of rate came up, that it's actually 10,000 times faster to react
Okay.
like this than to have the gas particle
Okay.
reaction. So traditionally, people have argued that all porphyry copper deposits happen below 600 degrees Celsius, but once they developed fluid inclusion heating stages which were capable of measuring temperatures higher than 600 degrees, they observed that they go all the way to 950 degrees Celsius. So it looks like this was a sampling bias, and that we have to think about higher temperature systems in order to address the formation of these deposits. So, to look at a very simple system, we chose a system which is conventionally used as a analog, which is the diopside-anorthite-albite system. As these are the most abundant minerals in most crustal rocks on Earth. So I did a range of experiments, most of the experiments that I show you today are from the diopside-anorthite system, but we also did some experiments with a sodium component in the glass. The experimental setup was fairly simple. We produced these glasses in a tube furnace, and then quench them, and then cut them in little glass chips, polish them on both sides to reduce surface roughness effects, and put them on a platinum tray to hang into the vertical tube furnace. And we did the experiments at atmospheric pressures from temperatures to 600 to 800 degrees Celsius over a range of different time scales to look at how these materials grow with time, to figure out rates, and also and always at the same constant flow rate of sulfur dioxide of 50 cubic centimeters per minute, which is a fairly high flow rate in these systems. So what do we expect? In the calcium end member system of anorthite glass reacting with sulfur dioxide, we expect a sulfate, a calcium depleted silicate material, and then some reduced sulfur. As we don't have any water in the system, we can't form hydrogen sulfide, and as the flow rate is quite high, we expect the reduced sulfur to be flushed away, and we don't expect it to stay in the sample. So we'll find sulfate layers on the glass, and below the sulfate we'll find some calcium or cation depleted region with diffusional or mass transport loss to the surface, and the sulfur dioxide moving to the surface. As this layer grows, the pathway for sulfur dioxide might potentially be limited. So the two major reaction limiting steps are either the movement of sulfur dioxide to the surface or the cation diffusion in the substrate. So how do these materials look like? This is a secondary electron SEM image of the glass chip of albite reacted at 600 degrees Celsius for 1 hour. So this is the polished surface on which the sulfates grew through the reaction with sulfur dioxide. These blobs, some of which have crystal faces, are the sulfate, so they're a sodium sulfate in this case. And in between we see gaps where we can see the glass which is not entirely covered. So at this stage, with these large grains, we thought we'll be able to do in situ isotopes of sulfur and so on. We can easily analyze them because they're so large. But unfortunately, this was not the case as soon as we changed the glass composition. At the same experimental conditions, the materials on the surface look very different. So this is on the diopside glass. You can see the scale bar 200 nanometers, and we have these almost amorphous looking little spheres of diameters of only 40, 50 nanometers. On the anorthite glass, we have more crystalline looking materials, but still they're usually less than a micron in size. So that makes the analysis of these experiments challenging. So we chose a range of different methods to look at bulk and in situ at these experiments. So initially we always used Raman spectroscopy to determine the phases on the surface. That can be a challenge because the Raman beam usually has a penetration depth of at least 3 microns, even if you're in confocal mode. If you have a transparent glass, it just goes on. Scanning electron microscopy can be also a challenge if you want to measure the composition, because the electron excitement volume is usually also about 2 microns deep. And so we also use the bulk methods to measure the composition of these sulfates on the surface. And then later on we did cross sections of the glass chips to measure diffusion and structural changes of the glasses. So what are the materials that form on these simple anorthite diopside systems? So this is, you can always see this these big humps. So these are Raman spectra of experiments at 600 degrees for 1 hour and 24 hours. And in almost all experiments, you can see these big humps, which are the bands, the broad bands of the silicate glass. Even though we see sulfates on the surface, it's very hard to see the peak here. But in showing that this glass actually reacted the least, others which have more material on the surface show sharp peaks of calcium sulfate and magnesium sulfate. After 24 hours, the material has grown so much that we can get a nice sulfate spectrum also on the diopside glass. But even though the diopside glass has the highest amount of calcium in it, we don't see any calcium sulfates on the surface at all. So calcium sulfates are only observed in this intermediary composition. So the first way to look at reaction rates is simply to measure the sizes of these grains on the surface. At the top is the diopside glass, and at the bottom is the anorthite glass. Looking at the sulfates on the surface, at 600 degrees Celsius after 10 minutes, 1 hour, and 24-hour experiments. You can probably barely see these grains on here. They have diameters of 30-40 nanometers. After an hour, they grow a little bit to about 50-60 nanometers. In about 24 hours, they're 100, maybe 200 nanometers in diameter. On the anorthite glass, the sizes are a little bit bigger, with 100 or so micron diameters after 10 minutes, growing all the way to almost 1 micron in diameter after 24 hours. From this, we can look at reaction rates, and we can calculate the rates. I'm not going to show you any numbers here, but this is how these plots look like. On the x-axis is time in minutes, and on the y-axis is the average grain diameter in microns. So down here we have 100 nanometers, and this would be half a micron or 500 nanometers. And we can see where we see a clear change in grain sizes on the anorthite glass, very fast growth in the first hour or so, and then not much growth later on. On the diopside glass, the change in grain sizes is much less profound. So from this, our conclusion of this observation initially was, well, if the grain size decreases so quickly, maybe it's actually the sulfur dioxide that doesn't get through. As the layer gets thick, it simply isolates the sulfur dioxide from getting to the silicates. So this is what happens with time. Looking at different processes with temperature is a very different story. Again, the diopside glass here on the left, the textures and the materials on the surface look very different. We get grains with diameters of multiple microns. So the rate of these reactions increases massively with temperature.
Does the surface of the glass stays glass, or?
It stays glass.
Okay.
In most cases, I'll show you a little bit on that. On the anorthite glass, also an increase of less than a micron to about a micron or so. It's less profound than on the diopside glass. And on the eutectic glass composition, we grow from at 600 degrees we have grains similarly sized as on the anorthite glass, but at 800 degrees the surface is completely covered, and it's a very rough surface because this layer is so thick that it becomes sort of wavy in shape. So before the images I've shown you before, looking at the effect of time, we can easily measure grain sizes and look how they increase. But as soon as we get different shapes of grains and different textures, it becomes very hard to compare simply grain sizes. And it's very hard to look at rates as a function of temperature for that reason. So we needed to use a different method. What we did is dissolve the sulfates of the glass surfaces into water, H2O, and we measured calcium and magnesium and some traces in these solutions using solution ICP mass spectrometry. And then in order to get a rate out of these concentrations, we had to normalize those concentrations and the amounts of sulfate that formed to the surface area. And this turned out to be very tricky because the glass beads are too big to use conventional methods for surface areas where you need, which you use to measure surface areas of volcanic ashes or so, because the surface areas are too small on these glasses. Hence we used X-ray microtomography at the Department of Applied Mathematics at the Australian National University. This is a 2D image out of the 3D scan, and the Department of Applied Mathematics has developed algorithms to measure all kinds of parameters in these 3D images, including laying a mesh on the surface of these glasses in 3D, which gives you the surface area. So from this solution data normalized to the surface areas, we can obtain a total amount of sulfate in moles per square millimeter of glass. I'm only going to show you results at 800 degrees, so this is 800 degrees for 1 hour. And on the x-axis we have the mole percent of anorthite. So this is the diopside end member, this is the anorthite end member. Here in the middle is the eutectic composition and another one on either side. Actually, these two glasses were chosen so that they have the exactly same liquidus temperature. And what we observe is that we see the same thing that we already qualitatively could observe on the SEM images, which is that the end member glasses have produced much less sulfate than the eutectic composition. And looking at this reminded me of simply the phase diagram of this system. Here in red is the liquidus temperature for these glasses. And for some reason, I expected that the glass would respond the reaction rate would be correlating in some way to maybe the degree of polymerization of the glass or the glass transition or some parameter like this. It's not at all the case because they would increase monotonously with polymerization in this way, but it's not the case. We have the highest amount of reaction rate at or near the eutectic liquidus temperature of the glass. So I don't know why this is the case. We are very close to the glass transition, in this case probably even slightly above, but why this correlation occurs, I don't know. So if you have some ideas, please let me know after. From these values at different time scales, again we can get calculate the reaction rates, and again we see that the eutectic composition has by far the fastest growth, and the two end members down here are much slower, but similarly at a similar scale. So to me this looked like the composition of the glass, and maybe the glass structure is limiting the reaction rate, and that would suggest that it's not the diffusion of sulfur dioxide through the sulfate layer which limits the rate, but actually the property of the glass itself. Which is why we went, actually only 3 weeks ago, I went to the nano-SIMS in Perth at the UWA to look at diffusional properties of those silicate glasses. And in this image, this is a cross-section of an anorthite glass reacted at 800 degrees for 1 hour, color-coding the counts for these two elements. So in red, you can see the counts of silicon, and in blue, you can see the counts of calcium. So we see the silicate glass here to the left of the interface. Here we can see in blue, sort of slightly porous sulfate layer. And then at the interface, we see very high count rate of calcium and a very low count rate of silicon. The other way around. Very high count rate of silicon, very low count rate of calcium. We can plot profiles through this, and we see some kind of compositional change towards the surface. A calcium depleted glass near surface layer, and then the calcium-rich surface material. The reason why I haven't tried to fit this to diffusion equations yet is that this is probably more qualitative than a quantitative observation, because nano-SIMS is very, very sensitive to properties of the glass. Matrix effect mean that likely this is depleted in calcium, so maybe this calcium depleted glass as a matrix simply allows silicon aluminum to be ablated at a higher rate. So it could be that these peaks of silicon and aluminum are matrix effect. Maybe there are some edge effects. I simply don't know, which is why I can't fit this to diffusion yet. So we need to look at matrix properties first. But qualitatively, we see the two reaction products that we expect. We see a calcium sulfate and anhydride, and below we see a calcium depleted silicate. Then I was interested in looking at changes of the structure of the glass, because losing the calcium, we'd expect changes in certain Raman bands where we should see change of the structure. And it turned out to be not the case. The only thing that we observe in terms of silicate bands is crystallization. So in this particular case, this is a stack of Raman profiles from the surface at a step rate of 1 micron to about 70 microns into the glass. So this is something like this. After about 20-30 microns, we see just the glass, and to the surface we see the crystallization of diopside in this case. And the interpretation of this is that the depletion of calcium and magnesium, this surface-rich layers, somehow destabilize this glass, allowing the crystallization from the surface. Looking at, I'm not showing this here, but looking at lower Raman wave numbers, where we would expect to see some properties of the coordination of calcium and magnesium, we didn't see any change. So we don't actually see any response of the Raman signal to this loss of calcium and magnesium, which is a little bit disappointing. Another neat thing
on this alumina silicate, do you supposed to see those two?
No.
No?
No.
Or excess silica?
Not really. Maybe the resolution is just not high enough. The problem with the Raman is that near the edge where we would see something, we get edge effects, so the beam is sort of scattered along the surface of the glass into the sample away, so that the signals are just rubbish. So this was, I find this particularly interesting, because we can also, in some experiments, observe sulfur going into the glass. So this fairly sharp Raman band shows sulfur as the glass. So we can, again, these are step distances of 1 micron between each spectrum to a depth of about 80 microns. And we see some sort of sulfur diffusion about 30 microns into the sample, and we can fit easily to a diffusion equation, and we get diffusion rates which for sulfur as sulfate is actually quite high. And it turns out from some estimates of how much calcium we lose and how thick these layers are of where calcium is lost, that both calcium and sulfur diffuse during these reaction experiments at a higher rate than you would normally expect from classical diffusion studies. So somehow the reaction changes the driving force of the calcium and sulfur movement, increasing its rate of movement. And to summarize this experiment, we have sulfur dioxide moving through a sulfate layer to the surface to react. There are two places where there could be a reaction occurring. I've only mentioned this one here, but hypothetically we could also grow the sulfate here on the surface, but that would also require the solid state diffusion of calcium through the entire sulfate layer, which would require an enormous chemical gradient, which we don't see within the sulfate layer, so I think this is not very likely.
Again, back to the question of Ken, you're missing one phase, the aluminum silicate phase. Where does it go? Al2SiO5. You have to have it normally.
No, so we don't directly observe it.
Why?
But it's probably not a pure phase, because it's probably just a calcium depleted surface layer. I don't know why we don't see it. On the nano-SIMS we see a layer which is depleted in calcium, but not with the Raman, and with the Raman it's probably just a resolution problem.
So some kind of amorphous, but not enough energy
Yes.
to crystallize.
Yes. Yes.
Oh.
So it's a aluminosilicate glass with just a low concentration of calcium and magnesium in it.
Much more viscous than the rest. So
That would
with
increase-
lower
yeah.
diffusivities.
Yeah. So that could block the reaction. So that could do that. But on the other hand, the rates of calcium and magnesium loss that we observe in these experiments is higher than what you would get from normal diffusion coefficients obtained from glass diffusion glass couple experiments, things like that that have been done in the past. So
if
why
you-
this is the case, I don't know.
So if you mass balance, normally the thickness of your glass on the surface of your starting material should balance with the amount of sulfate you have on the surface. No?
Yes. Yes, it does. Yeah. This is why we did the nano-SIMS, but I haven't had the time to analyze the samples. As I mentioned, the crystallization of diopside and in other experiments, anorthite, I think is an expression of a destabilization of this glass. A note of caution regarding the rates that we got from the grain sizes on the surface is that it's not only the growth of material that can increase or change that property, but it's also processes such as grain boundary migration within the sulfate layer, recrystallization, sintering, and so on that affect that as well.
Can you say something about, for example, number of the grain per surface area or something like that? Does it increasing, decreasing?
It decreases because
So
we get
there's a
larger.
coarsening.
Yeah, it's a coarsening. With time, we get larger grains.
So then your grain size curve might be dictated by
Yes.
completely different mechanisms.
Yes.
I see.
That's what I mean with this note. Hence, we are trying to determine the calcium loss from our nano-SIMS data, which I haven't done yet. And if it correlates with the solution data, then we can use those two values to compare it with the rates that we get from grain sizes, and we can see a difference and say how much of that rate is determined by overall growth and how much is determined by these kinds of mechanisms. So, as mentioned, we still don't have any reduced sulfur, which, just to finish, I would like to show how we try to catch it, which is simply by adding iron to the glass. So this is a iron-bearing silicate glass, and we were hoping that by having metals in the glass, these might move to the surface and be trapped as sulfides. Unfortunately, this did not happen. In turn, we get these enormous large anhydride crystals on this particular sample, with a length of multiple hundreds of microns. We get fairly large oxides after 1 hour, that is, and we get a mixture of sulfates and oxides in a fine-grained matrix. Among the oxides, we have both hematite and magnetite, mainly magnetite, but some hematite. We get a range of different sulfates, so the peak positions, there are multiple peaks, which is because of the presence of metals in the sulfates themselves, which broaden those peaks. And what I think happens here is that because the oxygen fugacity of sulfur dioxide is so high, if at all we form at some stage a sulfide, it's immediately oxidized by this high FO2 of the sulfur dioxide. In the substrate, again, we see changes. In this case, silicon is shown in green, iron in red, and calcium again in blue. We see the thin sulfate layer on the surface, and we see crystallization of oxides, but also of some other calcium-rich phase in the substrate. But generally, if you look at this layer here, there is a slightly higher intensity of green relative to blue, which is an increased ratio of silicon to calcium, again showing this calcium-depleted layer. I personally find it very interesting how the metals move to the surface, because it's not just iron that we dope those glasses with, but also a range of other trace elements. And we pretty much find everything from rare earth elements to moderately volatiles in the sulfates and the sulfides. So this reaction of sulfur dioxide with a simple basaltic glass not only forms a lot of sulfates in the surface, but it also somehow mobilizes metals such as iron and lead in particular also, by the way, moving to the surface, which might then more easily be taken up by a gas phase and transported to where it might be deposited or erupted. There are still a number of outstanding questions. The nano-SIMS data I haven't been able to quantify yet. We hope that we get diffusion rates out of these, and we also hope to be able to quantify and compare with the solution data how much sulfate we would have formed from this calcium and magnesium loss. And there are other questions such as how can we capture the reduced sulfur together with the oxidized sulfur in one experimental sample. So we, or Penny King in particular, is planning to do in situ experiments on the IR in a stage with SO2, looking directly at what kinds of species form during the reaction, and maybe do some sealed glass tube experiments to capture all those different phases as well. So in summary, sulfur dioxide is very reactive gas. Depending on the composition and structure of the glass, within 10 minutes we have a complete coverage of those surfaces at 600 to 800 degrees. We form both an oxidized and a reduced sulfur due to this proportionation of the sulfur dioxide. And it looks like the sulfur dioxide reaction rate overall is actually controlled by the silicate glass structure and not by the layer that we form on the surface. The reaction can change the glass structures to cause crystallization, and it can mobilize metals that can then be easier transported in a gas species. And finally, given the high abundance of sulfur dioxide in volcanic systems on the range of planetary bodies, remote or robotic investigations such as on Mars might actually show these kinds of textures of sulfates and sulfides together. That's it. Thank you.
Any questions?
Did you compare your research with a natural example of gas-rock interaction?
That's not part of my project, but Dick Henley is looking a lot at natural rocks, and he's been looking at a couple of porphyry copper deposits to look at textures, and often you find veins made up of sulfides and sulfates, and then you see sort of reaction horizons to the side which are less and less depleted in calcium. So we just submitted a study on skarns. So a lot of these porphyry copper deposits, the rich ones, are found in skarns around at the edge of those high temperature cores, and there we see changes of composition of garnets, of diopside, or generally clinopyroxenes, losing calcium as well. So it's not just simple anorthite diopside systems, but pretty much anything that has calcium in it allows that reaction to happen, and the sulfur to disproportionate and precipitate sulfides.
Because my experience is that reduced sulfur condenses immediately after sulfate. So you have the sulfate, and on the top of it, the cooler part of sulfate, you have the sulfur.
They're intermingled. So there's sulfate in the vein with little grains of sulfides in most cases. In that skarn study, which just comes to my mind.
Oh, it does not escape anyway, sulfur. Oh, much of
Well,
the sulfur.
the question whether this particular deposition happened, or whether the sulfur in this vein comes, whether the calcium in this vein comes directly from the rim there, is another question, because this is a long vein system where this calcium depletion into the vein happens. So maybe some of the reduced sulfur actually didn't form in situ, but was just transported from further away. But this is hard to prove. At least it's at the same time, because it's intergrown and it's in the same vein system. So whether the reduced sulfur that you form just there is deposited somewhere else is another question.
Is it only calcium-bearing sulfate?
Calcium is the one that forms the fastest, yes.
Because if you can come back to your solid solution,
Yeah.
If what you discussed here with the boundary and the kinetics,
Yeah.
and then it's very difficult to reconcile that kinetics, which seems logical, and that thing, where it's bizarre, because if you extract only the calcium, then you shouldn't have something that is symmetrical at all, because the
Yeah.
kinetics is going to be different. And if you have no calcium at all here, there is one.
So this is
So there should be
the sum of both calcium and magnesium. And
Can there be intermediate, like solid solution in a sulfide?
I don't know how much magnesium goes into this.
Because in those mixed systems, the composition of your sulfate is going to be very important relative to
Yeah,
the
that's
boundary
right.
that
Yeah.
forms in
Yeah.
between the.
I think about 10% of magnesium can go into anhydride. But the problem is in these, doing it by solution, you dissolve both the magnesium and the calcium sulfate. So it's hard to say how much of that. So in all those here, all those 4 experiments, we have a magnesium component in it. But how much of that is in the magnesium sulfate versus the calcium sulfate, we can't say, because doing the bulk method, we dissolve both. So it's hard to say how much was in the calcium and the magnesium sulfate.
because your interface is going to be magnesium rich or calcium rich, or it can vary actually with the sulfate you deposit on the top.
That's right. Yeah, I agree.
I had a question about the morphology of the grains.
Yeah.
Why is it so different between if it grows on anorthite or diopside? Is it rounded or crystal?
I don't know. I really don't know. I've tried to find out, but there's no correlation.
And there are no
There's on sulfates now.
On top of this is a polished glass, right?
Yes, so all these glasses are polished down to a quarter micron. Exactly to say it's not because there's some roughness there that causes different grains. Yeah.
But it's because it's not the same phase.
Okay.
One is the calcium bearing, in other cases.
Sure, magnesium bearing sulfate growing.
So it's not the same.
But these two here, on the diopside glass and the anorthite glass, we only detected. On the anorthite glass, we only detected calcium sulfate.
That's true.
There is probably magnesium in this. There is magnesium in this phase as well, because we detected with the solution But there is no magnesium sulfate on the diopside glass, which is odd because we find it on the other three intermediary glass. So it's not only the composition. Somehow the nucleation of a certain magnesium phase may be promoted by some structural glass surface property. I don't know. It's just speculating.
So, besides the sulfate diffusion profile in your glass, I didn't see any other indication saying that this is a transport limited growth problem.
Well, yes. That's why I went on the nano-SIMS.
Yeah.
And
Yeah, okay.
from those data, the idea is to try to obtain such diffusional data.
Because even the reaction rate limited growth, you can have this kind of zone boundary.
Right.
So, did you try to plot figure against the square root, the t square or something like that? Or?
No, I haven't.
That may be a simplest way
Yeah.
to show the diffusion controlled systematics. So, the other question. So, this porphyry problem are usually considered to happen in a magmatic condition, right? But for experimental reason, I believe that you decided to do at a lower temperature.
Yeah.
So, what happens if you do?
Well, no porphyry copper deposits have traditionally been suggested to have below 600 degrees,
okay.
400, 500 degrees. So
Yeah,
this is
okay.
not magmatic conditions. But recently, people have seen that it goes up to 800, 900 degrees.
Okay.
So in the window 600 to 800 degrees, it's exactly the window
Okay.
where we expect it to happen.
But then why basalt? You, in the middle of the talk, you actually try.
Because it's the simplest system.
I see, okay. Because you don't expect a 600 degree basalt. So.
No. Because it's the simplest system.
Okay. Understood.
Did you quantify the amount of sulfur in the glass? Does it diffuse through the glass? Or?
Yes, it diffuses up 30, 40 microns into the glass. Yes. So we did that with Raman spectroscopy. You can observe it about 30 microns into the glass in some experiments.
But this glass should be much less dense than the anorthite glass, or?
Yes, this glass here.
Yeah.
Yes.
So it could have a much higher diffusion.
But it's more
diffusion
viscous.
part. Yeah.
It's also more viscous.
It's more viscous.
Yeah.
It's solid. It's solid.
And your furnace is you're just blowing the pure SO2.
Yes, it's pure as. So the way we do it is when we hang in the experiments, first we purge with argon, and then and we let the sample equilibrate temperature for a few minutes. And we turn the argon off, and then we turn on the sulfur dioxide. and then after the time that we give it, we
Flush with argon.
we flush with argon again for about 30 seconds, a minute or so, and then we open and lift it out. And then we immediately put the tray into a desiccator.
Okay. Oh, I see.
Because a lot of, especially magnesium sulfates, they react, or they're extremely, they take the water immediately.
Is there any reason you didn't try to reduce the partial pressure of the SO2 or something? Mixing with argon or something, I don't know.
We haven't done that
Yeah.
yet, but that's so initially we were thinking about designing some flow reaction chamber where we can control the rate of gas flow.
Yeah.
But then there was just not enough time. This way.
Yeah. Just curious that how much is controlled by the activity of the SO2 available at the surface.
The reason why we have this high sulfur dioxide flow rate in the furnace is exactly to avoid the abundance of sulfur dioxide to be the rate limiting factor.
I see.
So if you mix in a lot of argon and have very low SO2 abundance, then maybe simply there wouldn't be enough sulfur dioxide.
So probably your reaction kinetics might complete.
Exactly. So we are way in excess of sulfur dioxide. So even if you over this hour, if you react the entire glass bead, take out all the calcium, we would still have enough sulfur during the experiment flowing through to reactor.
Yeah.
Yes. This is that's
At 800 degrees, you are above the glass transition.
just yes.
With iron, you are way above.
With the iron, yes. Yeah. That's why we did the iron bearing experiments at 700.
Okay.
Did you get crystals of alumina silicate on the on 1 hour? I understand, but on long duration experiments,
No.
never only glass.
No. Yes.
And in nature, is it described this
So
kind of phases?
In some porphyries which are rich in anorthite, you find a lot of mica, white mica, which is sort of the water-rich aluminosilicate. Yeah.
Yeah, actually, it could be a good idea to put water there also.
Yeah, but this just says the experiment, right? This is yes.
Yes. We should be the question.
So this is the
Tu veux boucher les tuyaux?
more natural.
D'hydrogène et de soufre dans le casseau ici.
Vas-y, moi je me casse.
Say again.
The CO2, for instance, we said in the natural systems, CO2 is not playing a role with calcium.
I don't think so, but I don't know. So we did experiments with marble, Carrara marble, reacting the marble with SO2. You get sulfate, and it's actually really a neat way to measure grain sizes and grain morphologies in the marble, because when we did the X-ray tomography, the interfaces of the grains light up really nicely because they have the sulfur in them. So that's how they measured the grain sizes of the marble, which wasn't possible with XCT before because everything is the same density. And then we put it back in the CO2 furnace, moved back to sulfate, moved back to calcite. And we did that 2 or 3 times. And texture remains the same, but it's just replacing one with the other.
Cool.
Yeah.
So, if the sulfur that is coming out from the magma chamber reacts with the surrounding, it means that how do you do to make a budget on the amount of gas that is actually coming out of the volcano? It means that. So it means that I mean people are measuring some SO2.
Yes.
But they often don't take into account all the sulfates that have crystallized.
Yes.
in order to make budgets. So it means that all the budget that are estimated are
Underestimating SO2 and overestimating H2S.
Overestimating H2.
H2S, because the reaction produces H2S, right?
Mm.
So if the H2S isn't depositing any metal, it's still in the gas, and it just increases the amount of H2S in the gas. So it might affect your ratio of SO2 to H2S.
So your main is in fact to try to quantify this effect in order to correct for the budget?
That might be one application, yes.
So how much correction can you guess? Can you give us?
No.
Are they wrong by 50, 90%?
No idea. No idea. Because there you have a whole number of other factors.
But you can tell by the amount of, if you have a way to geophysically map the amount of sulfate that has crystallized
that
in comparison with the lava that has been
But then you need to know how long the gas has been percolating through.
Yeah,
You need permeability, which changes during the reaction. So I'm not going to make a guess, but yes, that ultimately that might be an application of this. Yes. Another thing I thought might be an application is that if you're in a quiescent phase of a volcano and you still have gas flowing through, you might actually deposit some of the sulfur in the subvolcanic conduit environment, which can be re-released if you have an eruption, breaking down the sulfate at higher temperatures during the eruption. So that might be another way that might be a way to increase your SO2 or sulfur abundance in an eruption, because you just release all of the sulfur dioxide again, which has been stored previously as sulfates.
I have another question, maybe bizarre question. If the sulfur prefers disproportion in being at the 6+ and 0, why, or 2+? Why would it be as a 4+ in the fluid? Because it's bizarre, because if it's unstable as a 4+ in the fluid, it should be 6+ already.
Because it didn't have enough material to react with.
Why? Because it's in the chamber. They could react on.
You mean in the melt?
Yeah.
Because in the stability of sulfur or the
due to pressure, or due to
is also affected by the glass structure and by the way how it's incorporated in the melt and so on.
So you think in the glass structure it would be 4+, and then it would react on the solid phases.
It also has to do with conditions of saturation of the different phases, because you would to have. So I think in a silicate melt, it's usually 6+. And then if you release it from the melt, you have a redox reaction releasing it as 4+. So there's an entire other step, which is very interesting, but it's a different story.
Do you think you could apply this to other types of ore deposits like VMS, or would the conditions be completely different?
VMS has a lot of much more water in it.
Yeah.
So in VMS deposits, I think already. I'm not that familiar with other deposit types, but the ratio of SO2 to water is much lower. Hence, you already have. Hence, this gas buffer reaction is more efficient, and you have much more H2S already. I think, not entirely sure.
Any other question? Okay. Any bizarre question? Let's thank again.
That's coming.